computer. And let me put the time. So we're going to start at 10:12. And the first question will be from chapter 15, number 11. And I know you say part B and C, but I have a feeling to get to B and C, we have to do A. And so I will then, let's see if I can even remember. Let's see, how did I used to do this? Let me jump over to, first of all, finding the question. Okay. So here's the question now. Let me also see if I can remember how to do this. Share my screen. There's share. There's my iPhone. Good, good, good. And let me get the Bluetooth going here. Suppose I should have practiced this again. I was thinking I knew what I was doing, but maybe not. Okay. Oops. Nice. Okay. All right. Can you guys see my hand on the paper?
Yes.
All right. Thanks. Okay. So, and it looks like the camera would be better off. Slightly different angle. Maybe right there. All right, so I'll put here. So chapter 15, number 11. Let me scroll down here. Okay, so we have a 1/2 kilogram object. It's attached to a spring with a spring constant of 8 newtons per meter. It vibrates in simple harmonic motion, has an amplitude of 10 centimeters. A, calculate the maximum value of its speed and its acceleration. All right, so I'm going to maybe do a quick summary here, but the gist of what you should have gotten out of this chapter was that under the conditions of simple harmonic motion, which had that equation with the second derivative, and I won't quite go back that far unless you guys want me to, but this is the equation, and so taking the, I should say the equation of position, and so taking the derivative of that gives us the velocity, and the derivative of a cosine is, let's see, a cosine would go up, it would actually be a negative sine function, and the chain rule would bring the omega. And what the author worked out here then is, since the sine function goes up and down between plus or minus 1, then this thing out in front, the omega A, would be the biggest the speed ever gets. So, and now maybe I should do this kind of quickly because that wasn't your question. It says, what is the maximum value of its speed and its acceleration? So the omega comes from the thing that's in front of the second derivative. There would be a negative and something, and then the x. And since we're talking about a single spring, if we go back to physics 121, we say that the sum of the forces equals to ma. And since we're only dealing with a spring, the only force comes from Hooke's law, the spring. And when we rearrange this equation, we do have an equation that says acceleration being the second derivative. And so this thing out in front, this k over m, must be the omega squared. Because if you took this derivative twice, you would get the 2 omegas. So I guess that was kind of a quick review. But the bottom line is the way to get omega is then it would be the square root of k over m. So in this case, let me come back to the problem. The k is 8, and the mass is a half. Oh, good, they were nice to me, because 8 divided by a half is 16. Square root of 16 is 4. So they made a nice round number for me. So coming back to the maximum speed, which would be this omega A, I would have the 4, and the units would be radians per second. And the amplitude they gave, let me come back, and that was 10 centimeters. So that would be 40 centimeters per second. Oh, it froze on me. Well, that's a bummer. Glad I noticed it. Let me, before I go too much further. So, okay, why did it disconnect? Let's see. All right. Try that again here. Okay, so good. And it looks like it froze right as I was finishing up here. And so I don't think you've solved maybe these last steps. But again, I know that wasn't really your question. It got there. In fact, again, not part of your question is acceleration. And when you take the acceleration, which would be the derivative again. So let me take the derivative of this. So I'd still have my minus, my omega, my a, and the derivative of a sine is a cosine, and the chain rule gives me another omega. So again, one of the things that I hope you got out of the reading or the lecture or some of the video solutions I've been sending to you guys. I think you guys are 123. I think I've done 6 video solutions so far. So, this was asked in a number of problems. So in this case, it would be the 4 radians per second, and I'll square it together with the amplitude of 10. And in fact, let me put a page 2 up here just in case we need to come back and look at that. But that would be a 16, and a 16 times 10 is 160 centimeters per second squared. Nice. Okay, so find that and get to your question, Anthony. All right, so let's go on to B. I think we're going to need that information for part B. So B says the speed and the acceleration when the object is at 6 centimeters from the equilibrium. Now, let me make a very important comment. It's going to have to go back to physics 121 because in 121, if I did something like this, if I put maybe an object, I'll just make kind of a little baseball and say I drop it, and let's say it falls 3 meters. And the question is, what is the speed after it falls 3 meters? There's actually 2 approaches we learned in order to figure out how fast this object is falling. The first one, which would really be Newton's second law, would really be chapters 5 and 6. We said you could do something like this. Since you're given the distance it falls, I'll put x, you can get time. And because you know the acceleration, and now you've just found time, you can get its speed. And so that's kind of the approach you could take. Nothing wrong with that one. But when we got a little more advanced, we got into energy. And so maybe I'd call this approach the time acceleration approach. But this approach would be an energy approach, where we learned there was a direct connection between the position and the velocity. So it would be more of a one-step process to get there. So we have that same decision to make here in this problem. Do we go back to this equation, which gives us position and time, and say, okay, let's solve this based upon accelerations? And we could do that.
I did it that way.
Okay, or we could do energy. So I guess I should ask, what would you like me to do?
I did it with the acceleration, the finding the time, plugging into the x equation and then finding the time.
So would you like to see a different way, or would you like me to go your way?
Yeah, because when I did it that way, I ended up finding the wrong time, but getting the right answer. The time that I found for part B is the answer for part C, but it gave me the right answer for part B.
Okay, so let's go your direction. Okay, so I'll cross this out, and maybe actually that's pretty good, because I think one of the video solutions I did this one, and I did it in terms of energy, so I didn't do it this way. So that would be good to have both methods kind of video recorded here. Okay, so so I'm going to make this decision here that let's go ahead and use the equation for position, which is this A cosine omega t plus phi, and then let's use that to find time. Now, I do need to be a little bit careful here, so let me switch back over to the question, because this phase is going to come into play. Perhaps it depends if we need it or not. And given that I don't recall them giving us information to determine the phase, I'm going to conclude that what they ask does not matter. And so B says, find the speed and the acceleration. Yeah, so regardless of what the phase is, when it gets to a position of 6, it's always going to have that same speed. So that means the phase I choose here, or they're giving me that option to choose it. I could leave it as a variable, but I think if I leave it as a variable, that makes the math just a little more abstract. So I think I will do this. I think I will go ahead and say that this object, as it's going back and forth, back and forth, back and forth, why don't I say, oh, maybe that's the answer to our question. The time that you get would depend on the phase that you pick. So whatever time I get here is really kind of artificial. Okay? Because it goes with the corresponding phase. So when I put it back into the equation for the velocity, those two balance each other, which will give me the right answer.
Right.
Okay, so what I'm getting at is some people might pick a phase of 0, which essentially is saying the object starts right here at its maximum and goes back to its minimum, back to its maximum, to its minimum, to its maximum, like that.
Yeah, that's what I did.
Okay. Other people, and I noticed this in the solution, will pick a minus pi over 2. And to be honest, that's what I was about to pick. Because a minus pi over 2, if you a little algebra view here, would be something like this. If I plotted a cosine function, and to shift a function on the x-axis, in other words, if I had a function f of x, and I now have f of x minus a, you get the same shape, but it's shifted by a distance of a. So if I pick actually maybe a plus pi over 2 is what I was, I was thinking of minus pi over 2, because that would take this cosine function and shift it by pi over 2, so that would be to a sine function. Okay. And now I'm kind of debating which direction to go. Maybe I should go your direction, because I was going to say, well, let's just call the function a sine omega t. And if I, and I'm essentially then choosing my phase to be a negative pi over 2. Okay. But maybe to match you, I will do what you did, and you picked a phase of 0. And so your equation would be a cosine omega t. And we know that the a is a 10, and we know the omega is a 4. So let me do that. I would say that wouldn't be my choice, only because I'm looking at part C, where they asked it to go from 0 to 8, and a sine function starts at 0, so 0 to 8 is kind of my go-to picture, and that's why I would prefer the sine over the cosine. All right, but hey, why do it the easy way when we can do it harder? Okay? I'm joking there, by the way. You should try to do it the easy way. Okay, so knowing this then is the equation for position, and not worrying about C for a moment. It says the speed and the acceleration when it's at 6. So let me put in the 6, the 10, and the cosine of 4 pi. Now, by the way, maybe I'll put a little graph over here. Since I'm doing the cosine, this thing's starting at 10, and it would hit 6 in a short amount of time before it got to 0 and before it went to negative values. So it would be on its way towards the equilibrium spot. But that makes 8.6. That makes cosine of 4t. Then I have to take the inverse cosine. So let me get my calculator and check that I'm in radians, and go inverse cosine of 0.6. And I get 927 is 4t. Divide that by 4, and I get a time of 0.232 for the time it requires to get there. And like I said, that is kind of an irrelevant time, because it depends on when you started your clock at 0. What's important, though, is the equation for the velocity. So the velocity is the derivative of position. And of course, that would be the derivative of 10 cosine 4t. And so I'll put the 10 here. Derivative of a cosine is and I think that's the minus sign, right?
Yep.
Minus sign. And then the chain rule. So that's the minus 40 sine 4t. So I've already got the time still in my calculator. Let me multiply it by 4. Let me take the sine of that answer. It looks like 0.8. And so I'll go 0.8 times the negative 40. and I get a negative 32, and I've been doing units of centimeters per second. And that kind of makes sense back to my picture. It's heading towards the equilibrium. If I just kind of did a back to forth method, I would say I'm starting here and it would be heading back. So the speed would be a negative 32. However, I should probably point out when I read the question, it just says that when it's at position of 6. So if it had gone all the way to negative 10 and then came back around, when it gets to that 6, it would have the same magnitude, but going the other way. So I think a best answer is it's either a plus 32 or a minus 32. It could be, excuse me, it could be either one. There's nothing to, require that one versus another. Okay. All right. So let me come back here to the question. I just wanted to check my desktop to make sure my feed to you is still good. Looks good. All right. Okay. So then the other part of this was acceleration, I believe. Find the speed and the acceleration when it's at 6. All right. So the acceleration is the derivative of the velocity. So velocity was this one here. So when I take that derivative, I got the negative 40. Take the derivative of a sine, and I'm back to cosine. And then the chain rule, another 4 out in front. So that's a negative 160 cosine of 4t. And so now grabbing my calculator, let's see, looks like the 4t was up there. So I'll just do a copy and paste of that number. And then I'll do a cosine of that number. And then I will multiply it by the negative 160. And so that would be a negative 96, and the units would be centimeter per second squared. Now, maybe we should also check for pluses and minus, but I think this one's always minus because the acceleration is the same direction its force is, and the spring's always pulling it that way. So when at the beginning, when it is pulling it back to here, it's moving in the negative direction. So has a speed of negative 32. And it also is being pulled in the negative direction at a rate of negative 96. So that's why it goes faster and faster and faster. So the direction it's moving in the acceleration, if you remember from 121, are the same direction. That makes things go faster. So this thing's going faster in the negative direction. Of course, later on, it would go all the way down to the negative 10 and come back. And now, when it's going this way, when it gets to this spot again, it has a positive 32 centimeters per second. So it's going this way. But it's still being pulled that way. So the acceleration is still negative. And since they're opposite direction, it would be slowing it down. And sure enough, it would be slowing down before it came to a stop. So there is no plus or minus for this one. Okay. So hopefully that helps with B. But you were saying something about your time.
Yeah, I actually did that completely correctly. I think my mistake is with C.
Okay. I mean, that's fine. Hope I didn't bore too many people there thinking.
For part C, I plugged in the 8 centimeter it asks for into the X equation, but I didn't adjust my phase. I think that was the problem.
Oh, well, okay, wait a minute now. So you and maybe you can see it better in a graph picture. Yeah, your choice of phase would be this. You picked a cosine function. And I'll just write it again here. So x equals to 10 cosine 4t. So yours is doing this. It's coming down and going to equilibrium. then going negative, then coming back to equilibrium. So now it's at 0 going to 8, right? Right about there. This is what you want. You want 0 to 8. Then it reaches its top again. So what you want to find is what I'll call time number 1 and time number 2 and get the difference between them. And based on what you just said, although I kind of interrupted you, so maybe you didn't say the whole thing, is you just found the time it took to get to 8. And then that would be this, well, it would get to 8 here first. So you just found the time to go from the maximum 10 to the 8. That's what you found.
Yep.
You didn't find the 0 to the 8.
Mm-hmm. Which is, if I have a phase shift of the pi over 2, that should fix my problem.
Yeah, but let's, okay, but let's do it. I want to continue to do it your way.
Okay.
Okay, so let's do what you did. So what you first did is you did this. You said, okay, let's put in 8 here for the position. Okay, and you solve for time. Okay, so this would be points. Let me double check. Was it 8? Yeah, 8. So this would be 0.8, and then this would be cosine of 4t. And let me solve for t. So I would go inverse cosine of 0.8. Nice. Maybe I better do this in 2 steps. And then you would divide by 4 to get multiply by 4. Divide by 4 to get back to where it was. Divide by 4. Okay, so 0.161. Is that what you got?
Yep.
Okay, now, of course, that's not the answer, but it's useful. What that is it's the time to go from here to here. What I would really like, though, is 1 cycle later, 1 period later. I really want that time from 0 to there. So to find what I'm going to call t number 2, let me take this 161 and add 1 period to it. Okay, 1 cycle. And of course, the period I haven't solved for, but the period is 2 pi over omega. So 2 pi divided by 4 is a time of 1.571. So let me add to that 0.616 and get 1.732. Okay, so what on my graph, to make it clear, what I've gotten is the time. So it started at its maximum, went to equilibrium, went into the negative zone, went back to equilibrium, and now this is the part I'm interested in, from 0 to 8. Okay, so 0 to 8, and so I have just found time number 2. So it would, if I did a back and forth method, it would start here. Oh, my bad. Sorry, 1 whole period would be when it came back to here again. Sorry. Sorry. Glad I saw that. Nope. Sorry. Forget what I just said to there. All right, so let's go back to what we did find here. So what we did find is the time it took to go from here down to there. So what we need to do, is let me pick the top of it. The time to go from the top down is the same in reverse here. So Actually, maybe I should just do the time from there to there. That would be the same as there to there.
Can you find the time from the top of the cosine to the equilibrium point on that first iteration, and then subtract t1?
Yeah, I'm just debating myself if I should do this. If I found the time between the 8 and the 0, that would be the same as what they're asking, which is the 0 to the 8. Okay. So since you saw that, I'll go in that direction. I was about to move it, because if we took one period and subtracted this time, that's what I should have done. I should have said time 2 is 1 period minus 0.16. So it should have been 1.5. Anyways, but let me go your direction. Be a little bit easier. And so let's then know that, well, and for labeling, let me call that time 3. So what I've really found is right here, time 3. I found the time it took to go from its maximum to this 8 centimeter. And then right here is, let me call this time number 4. And so let's use that same equation and say, okay, it equals at 0, 10 cosine 4t. Divide by 10 and I get 0. Take the inverse cosine, so 4t equals pi over 2. And that means t, and this would be t number 4, would be pi over 8. Let me put that as a decimal. So pi divided by 8 is 0.393. So if I take time 4 and subtract time 3, so 0.930 minus 0.161, I get a time of 0.232 seconds. And out of my own curiosity, let's scan the answers here. Which this is our first one here today, so I guess I haven't called up the solutions yet. Let's go.
That's correct. They did it a different way, but.
All right. Oh, good. So it is correct. Let me see what they did. Okay, so they did use the time method. They didn't do the energy method that I was thinking. But see, what they did is they picked a phase that had made it a sine function. So they picked the minus pi over 2 that I was talking about, which, again, the advantage would be you don't have to do 2 calculations of time and subtract them to get the change in time. You just have to do 1 calculation of time. So I'm sure that's why they kind of picked it. However, they should have done a better job and explained why they're picking that one, so that you can see you kind of have that freedom of choice.
Thank you.
Awesome. Okay, so let me get myself a little more organized here, and I'll jump back over here to the chat room. And let me say it again. I know a couple people have popped in and out, and I just want to say that when I'm working on these, I know the only way I can kind of keep track of who's next in line is throw your question in the chat room. Okay, and so toss it on up into the chat room, and I'll scan that way. And so until 10:45, this is kind of going to be new for me this semester. Till 10:45. I'll move anybody in 121 kind of up to the front of the line. But if this semester is a repeat of like last semester, 90% of these questions are going to come from 123. So anyways, any of you out there in 121 or 102 got one, shoot it up. If you're just kind of checking out, that's fine. If you're just doing an observation, like my buddy Don here, that's great. All right. All right, Allie, right? Am I saying it right? Did you go by Allie? Yeah, okay, I thought so. Okay, could you explain number 21 and 15? I could. Let me write down the time. 10:45, chapter 15, number 21. So chapter 15, number 21. That way when I send out the recordings, somebody may want to just kind of fast forward to this time in the video and watch number 21. Okay, so let me take my desktop and find the questions. Number 21 says, a cart is attached to a spring with a spring constant of 3.24 meters per second. It vibrates such that the position is given by this function. Let me write that down. So x equals, and so there's the amplitude, 5. I'm not going to write the centimeters, but it's in centimeters, times the cosine of 3.6 t. Okay, and they also did give me the spring constant. We write that 3.24 newtons per meter. Okay, and just for my own mental thoughts, since it's a cosine function, it would start at its maximum and then go to its minimum and then back to a maximum and then to a minimum and then to a maximum, okay? And so a cosine graph would look like this. It would start here and do that kind of thing. Okay, so this would be something like literally just pulling it and then letting it go. Right when you let it go is when time equals to 0. So our phase in our equation is 0 for that one. Okay, so it says during the first cycle for t greater than 0 but less than 1.75 seconds, at what value of t is the system's potential energy changing the most rapidly into kinetic energy? Ooh, okay. Okay. So maybe parts of this before I get started is to measure the amount of time. So this is the time axis for one cycle. So the period would be 2 pi over the omega. And the omega is this little part of the equation with the trig function. And so this is the 3.6. So just out of my own curiosity here, 2 pi divided by 3.6 is the 1.75 seconds. So now I understand a little better why the author says between this time frame, so in one cycle, so as it goes from here on back and forward, when is the potential energy changing the most? Okay. And by the way, just to be a little careful here, it does say it's changing most rapidly. So it doesn't say if the potential energy is changing and getting bigger or changing and getting smaller. So I think we're going to have to include both of those. All right, but let me just get to potential energy. So potential energy from a spring, and I have to remind you of Physics 121, Chapter 7, is this 1/2 kx squared. So if I put in this 1/2 and the k of 3.24, and the equation for x, which was given as 5, and I probably should be a little careful with units here. This is newtons per meter, whereas they gave me centimeters up here. So if I put it in as a meter, and square it, that's where I will get one of these meters to cancel down here. So I'll be left with one more meter and a Newton. And a Newton times a meter is a joule. And so we're going to have units of joules for our potential energy, as we're accustomed to. Okay. So grabbing my calculator here, I'll take the 1/2 and multiply it by the 3.24, multiply it by the 0.05 squared, and get a number of 0.00405 joules, and then cosine squared of 3.6t. And again, I don't know if a graph is necessary, although I like to think in terms of pictures and graphs. So notice it's a cosine squared, and a cosine squared starts at 1 and does this kind of thing. It doesn't have any negative values. That's because you're squaring it. So when you compare it to a cosine function, this part would be from here to here. Then all these negative numbers would be this part. And then it would go positive again. And so this here would be the 1.75 seconds. And so it looks like it would start with a lot of potential energy. Makes sense. It's pulled to the side, a lot of potential energy. Then it would lose it, and it would have no potential energy when it got to the equilibrium. Again, hopefully that makes sense because the x would be 0 there. Then it goes in the negative direction. Its potential energy would gain, because again, as long as there's an x value, there's potential energy and it's positive. And so it would reach another maximum at the negative side. Then it would come back and reach equilibrium again. That's where its potential energy would go to 0, and then it would go back to the positive side. And so you would have three if you count the beginning. So the beginning, and then when it's at the negative position, and then when it's at the positive position. So that's where it would be its maximum. It would be its minimum here. But either way, the question asked, where is it changing the most? Well, it would be changing the most where the slope is the most. And so right about here would be the biggest slope decreasing, biggest slope increasing. Then there'd be a big slope decreasing and a big slope increasing. In my picture, that would be here. So somewhere as it is racing back towards here, maybe right about that location, it's losing the most potential energy. And then the mirror effect, when it gets right about there, is it's now gaining at the same rate as it was losing. And then it goes to the negative side and comes back, and then it's going to be losing it at that same spot. And then it's going to come over here and gain it. So in one cycle, there should be 4 places here where it's changing the most. Twice losing and twice gaining. All right. So now this kind of becomes a math question because, how do you, determine, when something is changing the most? Well, what they're really asking then is, how does the potential energy then change with time? So they're not asking for the most energy. They're asking for the most that it is changing. So I need to find the equation that represents the change in the potential energy. You might call that the power of it. But let me just leave it as the rate at which the energy is changing. Okay, so I have the derivative with respect to time. And let me just get that equation back onto the screen here. But there it is, 0.00405. And then a cosine squared of 3.6t. So if I take the derivative of that, constants pull out in front, so I'll just leave that one alone. And the derivative of cosine squared would be 2 cosine, and then the chain rule would be the derivative of the cosine. Derivative of cosine would be a minus sine. Maybe I should have put the 3.6t in there, 3.6t. But then I guess I would have the chain rule of that, so there'd be another 3.6. Yeah. Do that right? 2 cosine, and then the derivative of the cosine, which would be a negative sign, and then the chain rule. Okay, good. All right. Now, I'm going to go ahead and move this around a little bit. I'm going to put the -1 in the front. I'm going to leave this 0.00405 alone. I'm also going to move this 3.6 to the front because I think what could be helpful is to recognize that trig identity. That 2 times cosine times sine is the sine of 2 omega t. Or in this case, omega is 3.6. So 2 cosine x sine x is equal to sine of 2x. And let me do this as a little shout out to your textbook. Remember, that's why Appendix B, at least in the survey, and I think the OpenStax has the same thing, it's got a nice set of mathematical reviews. So as you come across derivatives or trig identities in this case, it's a good place to jump on. So with that in mind, I could then, and maybe I should put all this together here. So this is a negative, and so that's 0.00405 times the 3.6. This would all be a negative 0.01458. But the big thing right here is the sine, and 2 times 3.6 is 7.2t. Okay. So this right here is the rate at which the energy is changing. And of course, it varies with time. Now, let me come back here to the question. It says, during the first cycle, at what value of time is it changing the most? Okay, so whoops, let me fix my computer there. Okay, so the if I say this right, changing the most would be this value, 0.01458. Now, since they don't say whether it's increasing or decreasing, I think we've got to then say, really, at what moments in time would the rate of change, so the rate of change, when would it equal either a plus or a minus 0.01458? And so that's really what it said. I knew that thing would interrupt my screen. Bummer. All right. Let me try it again here. Yeah, good. Back to some faces. Got some new people in here. Hi, Hunter. Okay, so let me share my phone again here. Okay. All right. Good. I should have looked a little closer when it froze out. But what I was trying to say, and this problem gets a bit wordy and mathematical, I think, because we first had to find the potential energy, and so now we're looking at the rate of change. So we've got the rate of change right here for the potential energy, and they want to know when it's a maximum. So when it is this plus or minus, and I think maybe the better way to solve this one would be to kind of make a graph now of a sine function. My red pen dying. Grab a different one. Okay. And a sine function, I think, as you know, goes up here, and that's its maximum. Then it goes down to 0. Then it would go to a minimum and then back. And that would be one cycle, but remember, we're at twice the frequency, so we do this again. So it would happen here. And so 2 cycles of this sine function are the same time allow for 1 cycle of the actual physical motion, right? Because it's the energy squared. And I said, so there should be 4 places, a maximum decreasing, a maximum increasing, a maximum decreasing, and a maximum increasing. And so that would represent here on this sine function, this would be the oh, I'm sorry, I plotted the wrong function. This should be a minus sign. Let me try that again. It's a minus sine function. So it goes down first and then up. So that's why the first one is a negative. That would correspond to the energy right here, the maximum decreasing. Then it would come up here to this spot, which would correspond to here, the maximum increasing. And it would come down here to a maximum decreasing, and then finally a maximum increasing before we complete 2 cycles for this function. But that is 1 cycle for the wood block to actually go back and forth. So it would be at here going left, here going left, here going right, and here going right. So there should be 4. 1, 2, 3, 4. And this is kind of easy because we know this one right here is pi over 2. And so when 7.2 t equals pi over 2, we know this one right here is, I guess I have to think about this. Is this 3 over 2 pi? 3 over 2 pi, because this would be a pi and another half, yeah. Okay, so when that equals 7.2 t, and we know it would be here, so that'd be 5/2 pi. So when that equals 7.2 t, And then the last one would be right here, which would be 7/2 pi. 1, 2, 3.5, good, would equal to 7.2 t. So when 7.2 t is equal to pi over 2, that would be one answer. So this would be the first answer. So grabbing my calculator, pi divided by 2, that answer divided by 7.2. So this would be 0.218. And then this one over here, which would be 1.5 pi's divided by 7.2. So this would be when time is equal to 0.654. And this one here, which would be 2.5, I'm just going to edit my calculator, 2.5 pi divided by 7.2. So 1.09. And then the last one would be 3.5 pi. So 3.5 pi divided by 7.2. And that would be a time of 1.53. And then the next one would be out of the range, because if you remember early in this problem, they said, hey, make, one cycle, don't go past 1.75 seconds. All right, so there's the fourth one, the third one, the second one, and the first one. That had a lot more trigonometry in here than I kind of anticipated. Let me jump over to the solution. What number was this? 21. Let's just hope I did it right here. So they say 21. This gives 0.218. And then they did the 109. How come they didn't do these? Oh, my bad.
For that one, I'm getting 0.65.
Point for this one here?
Yeah.
Yeah, and that's what I got. But you know what? I think I was a little careless. Let me go back and read the question carefully.
Okay.
Because when I got to this point, I said this would be the point where the potential energy is decreasing, and this is where it would be increasing. And I did say something wrong here. I said the author wasn't clear about whether it was increasing or decreasing, but let me read it again. And I think the author is clear. I was careless here. Watch. Where does he say it here? He says, during the first cycle, for what value of T is the system's potential energy changing the most rapidly into kinetic energy? And that was important. It wasn't just changing, it was changing into kinetic energy. That means it is losing potential energy. So the author is really only asking for the spots where the potential energy is decreasing the most, not increasing the most. So these values where it is increasing the most, he's not asking for. And that's why the solutions only have these two, because it's these two where the energy is decreasing and going into kinetic energy. The potential energy is decreasing and going into kinetic energy. It is at these points where the potential energy is changing by the same amount as here. That's why I put them as answers. But it's changing in a way that it's going from kinetic energy into potential energy. It's going opposite of what the author has asked. So these should not be the answers. So I apologize for that. He did make it clear, and I overlooked that little subtlety here. So I'm glad I kind of looked at the answer. He only gave 2 answers instead of 4. Nice. Okay, now I think there's more to it, if I'm not mistaken. We come back here to the question. And I'll probably need another sheet of paper here. But I believe there was a part B. It says here, part B, what is the maximum rate? Oh, good. Now that's going to be easy because I actually already addressed that. Let me come back here. When I worked out the equation for the rate at which the energy is changing, and not set it equal to its maximum. I said that's the maximum, but that's it. And the number out in front would be its maximum. So I guess that number out in front is 0.01458. Let me check that answer. And, oh, wait, we disagree. Oh, he goes, okay, yeah, so I'm in watts. And so if I move the decimal 3, 14.58 milliwatts, which he rounds to a 6. So he used 14.6 milliwatts. Okay, good. Yeah, so we agree there. Yay. All right. Great question.
Thank you.
My pleasure. These are fun. Hope you find them fun. Okay. A bit tricky, a bit mathematically or trigonometry intense. That's probably the biggest warning I could have and should have given you guys is that the problems aren't really so hard because are at least compared to what we did first chapter last semester. That was a killer of a chapter to start the semester. And a lot of trig. A lot of calculus. This one just starts with a lot of trig. So it's probably a good exercise of maybe more reviewing your trig. That, by the way, that's kind of what I've noticed. The students who have a little struggle, it's what they're struggling with is more with the math and the physics. They're like, oh, I kind of forgot all my trig and my trig identities here. Okay, so let me jump back to my Zoom here and see. Camera's still good. All right, my feed's still good. All right, and we'll go to another question. All right, so next on this list, and maybe I'll just save a little piece of paper by drawing a line there. I haven't used much of this. So could you go over number 49? Yes, I could. Let me write that down. So course, chapter 15, number 49. The time is 11:15. Nice. Okay, so chapter 15, number 49. Okay, and let's me now find the questions again. All right, scroll down here. 49, 33. Oh, 49 must be the second block on top. Ah, yeah, didn't copy real well. Maybe I should make a better PDF of this. We'll, yeah, too late now, but know that the problems, if you have troubles with them, are also listed in the, or they're in your textbook. And that's good or bad. I like this because they're all in one place. Also, maybe it's good because when I have them scanned in black and white like this, you don't really know which one is the blues and the magenta ones. So maybe it won't intimidate you when you, if you don't know what color it is, if it's supposed to be easy or hard or medium. All right, but let's give this one a try. And like all these ones, they're kind of rooted in Physics 121 and then going on to our new stuff here. But this one has this block that sits on top of another block. And it moves along, that is the top block moves along only because there's friction between the two. See, the bottom one is being pushed back and forth with this spring. In fact, if I read the problem, it says here the large block, so this one down here, and P, and I think if you look at the better picture of this, you'll see that that says P. Anyways, executes a horizontal simple harmonic motion, and it slides on this frictionless table. So there's no friction down here. And because of that, we know from this chapter that we have this simple harmonic motion going on back and forth. And let's see what information they give us here. With a frequency of 1.5. So the frequency is 1.5, which means the omega, which is 2 pi f. The angular frequency would be then 2 times 1.5, so that would be 3 pi. So we would know that much. Block B, I'm sorry, did I miss something?
Bryce. I think your camera.
Wish I could figure out why it does that. Let me try this. I wonder if I just re-hit it on my phone without stop sharing. My phone's a little confused. My phone thinks it is connected. So now it's just swirling and looks totally lost. Oh, wait. Huh. And I'm just going to go stop share. Okay, so let me try it again. So let me go share. Share. And see what happens. And hopefully I didn't make it worse, because it's still kind of just locked up in a spin here. Oh, my bad. I tried to. All right, well, I'm going to do stop sharing. And what happens? Oh, I stopped this thing from hunting. Please stop. Okay. Mind if I turn off the Bluetooth here? Let's go to settings. Bluetooth. Turn it off. Turn it back on. Nice. All right, well, I'm going to try that. Let's see. All right, so screen, share. Hello. Yeah, I think I really screwed it up when I asked it after it crashed to hunt again for without stop sharing.
Yeah, Zoom problems are always fun.
Yeah. me stop sharing, and if I just turn off my phone. Try this. All right,
No,
so I'm gonna turn off my phone here. Might have to get the whiteboard out here. Yeah, electronic whiteboard. That'd be cool. But I'm gonna do this one here. Okay, so that's probably long enough. Now I'll try to boot my phone again. And give that a chance to get going. And if this isn't long, I'll leave it alone. Otherwise, I'll switch to my whiteboard. Let's see. Do I got my stylus? Oh, good. I got my stylus.
I remember you used that a couple times last semester. Did that just not work out as well as the phone?
I don't know. Actually, I think that's a question more for you guys. I thought it came out pretty good, actually, the whiteboards. And what actually was really nice is there were times where I preferred the whiteboard, yeah, because I could copy and paste an image right out of the textbook, and place it right on there. And a lot of that stuff was visual. Yeah.
I used something similar.
Yeah, so now that I talked so much, my phone rebooted, so I won't even try the whiteboard here. Okay, so let's see what happens when I go to share my phone and my screen. That acted much better. And yep, there it is. And let me go to my camera. Nice. All right, let me remount it then. Okay. Yeah, I was thinking about that whiteboard, and I was like, but I didn't think there was anything that needed any kind of visual effects as much as all those flux pictures we had last semester. Okay, so finally getting back into this, I'm not sure exactly where it froze, but I was trying to come up with the equation here. Knowing that it goes back and forth, we can then get the omega because they directly give us the, I'll call it the regular frequency or the linear frequency. So if I multiply 2 pi, I get the angular frequency, and that's the mathematical piece. So going from the physical piece to the mathematical piece, so we can actually have an equation. Now, they don't give us an amplitude here, and that's really why, because they say this top block B, so block B rests as shown in the figure and has a coefficient of static friction, so mu sub s as 0.6. What maximum amplitude of oscillation can the system have if block B is not to slip? Okay, so going back to physics 121, static friction was this inequality. Static friction was less than or equal to the coefficient of static friction times the normal force. So as this goes back and forth, block B, as it goes back and forth, has to have a certain amount of friction, which corresponds to that acceleration. So what I'm saying here is we need to make the force of friction needed to make block B always remains less than this. Now, also keep in mind that the only thing moving this block is the friction. So if we also say you add up all the forces and you set it equal to MA, we're saying that the whole force on it is the static friction, and that has to equal to MA. So if I put this into here and write it over here, we're saying that MA has to be less than or equal to the coefficient of friction times the normal, or the acceleration has to be less than or equal to the coefficient of friction times the normal divided by the mass. And so that's the stuff that I'm getting from Physics 121. Also from 121 is I can get the normal force, because if I draw just block B by itself and realize that gravity is pulling it down, so mass of block B times G, and normal force coming from block P is pushing it up, and the frictional force is sideways. But when I add up the forces in the y direction, normal force minus mg has to be 0. So the normal force is mg, and I'll use that in here. Although I'll move on to another page. So I'm saying acceleration has to be less than or equal to coefficient of friction, and then putting in the normal force would be mg, and then divided by m, so the m's go away. So this is saying that for this to work, the acceleration of block B must always be less than coefficient of friction times g. And really at this point, I would say I've only been doing stuff from 121. But now I need to tie the two blocks together, because then if block B is going to move along with this block P, and so maybe I should have put a B here, I would say then that block P would also have to be less than that number. But maybe I'll hold off on that, because block P is going under simple harmonic motion, and the maximum acceleration of something in simple harmonic motion was one of the things we derived there in the book and in the lecture as omega squared A. So putting that over into here by saying that block P would have to have the same acceleration as block B in order for them to stay together, then I could say that omega squared A must be less than or equal to coefficient of friction times G. Or what we're after is A must then be less than or equal to coefficient of friction times G divided by omega squared. And now that I need to come back, I kind of got lost there when my screen froze, but it says, what is the maximum amplitude? Yeah, and so for it not to slip, the amplitude has to be less than that. So the maximum is when it's equal to that. So let me put in my numbers now. Coefficient was 0.6, G is 9.8. Omega we found back on page 1 here as 3 pi. So I'm going to square it. And now I'll grab my calculator here. So 0.6 times 9.8 divided by, I'll do it separate. 3 squared is 9, and pi squared is just pi squared. And so we're looking at 0.066, and I believe I'm in units of meters. Let's see, meters per second squared radians per second. Yeah, so this would be meters, which would be 6.6 centimeters is probably how the author is gonna list it. Let me switch over to the solutions, and 6.62 centimeters is what the author has. Ah, good. So hopefully that helped. Nice. All right. And let me jump back to the chat room here. Let's see, that was Hunter or Daniel. Oh, I'll be back later today. Okay, good. I figured you would. Oh, and timing's really good. This is kind of our first break, huh?
Mm-hmm.
All right, so let's take our first break. It's 11:30, and we'll come back and let me check my stuff here. Yeah, 12:30, and give priority to 121 people if anybody's there in 121. Who's got a question? They're obviously just converting units right now, so I don't know how many questions they're going to have. It's not nearly as hard as the trig functions you guys are doing.
Awesome. See you then.
All right, take care. And we'll see you guys in a little bit if you come back here.